Thank you, Paul. Is my presentation full screen?
Yeah, we can see it.
Okay, thank you for the invitation to talk about this topic. I'm here to give you an overview of a review paper, so it's kind of like a meta overview. I have been collaborating with a group of faculty and postdocs at MIT on this project that is funded in part by MIT and in part by CMIP Sciences. And the project itself develops emulators. My task was to write a review of the field to help guide actually, future directions. So the paper is actually out, at least online. You get here, a couple of pointers to it. It's not open right now. It will become available without subscription as soon as the issue of the journal gets published. So the first thing we wanted to do was to frame our interest in these emulators by specifying what type of emulators we are talking about. Because as you know, probably, people use the term emulator for many different types of tools. So we are trying to clarify what our interest is by this diagram that portrays, the flow of information, or if you want, the stages of modeling when we try to connect human activities, human systems to Earth system outcomes and vice versa. So, the usual way to do this is to have a representation of, human activities, sectors that produce emissions and land use change. Those emissions and land use change result in concentrations of active gases in our atmosphere and determine radiative forcing. That in turn affects the climate, and the climate outcomes affect human systems in turn by, causing impacts and risk. So in this framework, we use, specific modeling tools to go from one box to the next. So we usually use integrated assessment models or multi-sector dynamic models to go from human activities to emissions. We use simple models, perhaps, like MAGIC, FAIR, Vector, to go from emissions and land use to radiative forcings or concentrations of those gases in the atmosphere. Then we use climate models to go from those concentrations to climate outcomes, or more recently, we may skip that intermediate step and use Earth system models with an active carbon cycle to go directly from emissions to climate outcomes. And this way also represent possible biogeophysical feedbacks of what changes in climate mean in terms of changes in the ability of our natural carbon sinks to absorb some of those emissions. Once we get a representation of climate changes as a result of human activities, we want to translate those in impacts on things that we care about, on assets, on infrastructure, on human health or ecosystem health. And once we do that, we may be interested in representing another type of feedback, which is what we call socioeconomic feedbacks, where we may want to ask, are those impacts large enough to affect the development of human systems, especially the size of the economy, and in turn change the size of emissions that would be otherwise produced if those impacts didn't exist. Okay, so if we don't have any problem in deploying computational resources, we may use all these different type of models to create these consistent and coherent and integrated modeling setup. But more and more, we realize that we cannot afford to run costly, especially Earth system models and climate models for any possible scenario that we may be interested in. So we can substitute emulators that either allow us to go directly from emissions and land use change to climate outcomes and possibly represent those feedbacks, or may use, again, simple climate models to make that intermediate step and then just translate concentrations of greenhouse gases into climate outcomes. So these are the kind of emulators that we were interested in reviewing and try to make, a map of the landscape that is changing very, very rapidly in the last couple of years and continues to do so. So why is that happening? Why is this sudden, mushrooming of type of emulators, interest in emulators? And we decided to split, the reason into two pieces. We argue that the demand for climate information that emulators can meet is becoming larger and larger. So, more need for climate information for impact modeling, decision making, policy making, and also simply communication. Much beyond what, complex climate models can handle in terms of the number of scenarios that people may be interested in assessing and using. That's where climate emulators, climate model output emulators can come to the rescue. From the supply side, we argue that we are in a new era of both, unprecedented computational capacity and tools that make that kind of work, the development of emulators, much easier than before. But also, thanks to projects like CMIP, we have a humongous amount of actual climate model output on which we can train those emulators. So there is this, fortunate convergence of demand side and supply side that makes the development of emulators so much faster and so much more, numerous. Now, just one more slide to talk about why we use emulators. So I mentioned this idea that, we need climate information for scenarios that are more than just those that handful of scenarios that CMIP can ask climate models to run. We also are more and more interested in exploring internal variability to characterize, the noise in the weather and in the climate. And that's another aspect that can be addressed by a good emulator. We may also be interested in lightening the computational burden of modeling centers so that they can run a limited number of scenarios and emulators can fill the gap or can, add initial condition ensemble members to an ensemble already in existence or create a whole new one. I mentioned, the idea that when we want to represent this interaction between human and Earth system, there is this complex modeling, framework that we need to represent. And we may want to use integrated assessment models to do the whole thing, but to do the whole thing, these integrated assessment models need a representation of Earth system changes. And here is where emulators can help by doing that without burdening the computational, aspect of the modeling, like a real Earth system model would do. And then, as I mentioned, it's not only about modeling, about research, but it's also about communication, about policy and decision making, about education, where emulators can help, explore different scenarios and different realizations of climate and at a cost that is much lower than using an Earth system model. And along these lines, somebody has talked about emulators as a tool that facilitates a democratization of climate modeling, which is still, for the most part, the domain of, rich countries like North American countries or European countries. Now China is developing climate models at a pace that is, strong, but still it remains for the most part global north type of enterprise, and emulators could help fill the gaps that leaves. So in the paper, we try to characterize and categorize the type of emulators that are out there in the literature. In this presentation, I'm not going to go into any technical details. The paper is there, or if you cannot access, send me an email and I will send you a copy. We decided to categorize emulators into 5 different categories. Pattern scaling has been proposed starting from 1990. It's still very popular. It's still very valuable as a, underpinning of more complex emulators. So there is pattern scaling. There is a whole category of emulators that have taken pattern scaling and taken it to the next level, enriching the methodological approach significantly. There are emulators that are based on other type of sophisticated statistical modeling. There are emulators that are actually more based on dynamical system understanding and theory, like impulse response type of emulators. And then there is the whole category of machine learning based emulators that is really taking over in the last couple of years, I would say. We also try to review what are the drivers that are needed to make an emulator produce climate output similar to spatially resolved and time frequency resolved type of model. Most emulators are driven by either greenhouse gas emission pathways or their translation by a simple climate model into global temperature pathways. But the most recent machine learning emulators are actually trying to mimic the dynamics of a climate model. So they need initial conditions or boundary conditions similar to what a climate model needs. Except then, their integration forward is much more computationally efficient, fast, and cheap. What we found is that still we lack a robust understanding and modeling of what emulation should do when the forces are not just well-mixed greenhouse gases, but are things like land use or aerosols that are regionally and time varying. What do emulators emulate? Well, thanks again to these machine learning emulators, we are getting more and more skillful emulators that produce high frequency, like daily or even sub-daily variables, maybe even multiple variables jointly. But the most common output of emulators until a couple of years ago was actually just temperature or precipitation, sometimes jointly, but most often not at monthly scale. We also make the point that usually emulators are trained to emulate a specific Earth system model, but lately also we see emulators that incorporate observations that try to do bias correction of that model output, or are used to downscale the model output that usually comes at the 100-kilometer scale to much finer local scales. It's true that emulators are still very, very much confined for the most part to atmospheric variables. We don't review emulators that are specifically developed for individual processes, and the most common example of that are emulators for sea level rise or ice sheet behavior. So we conclude our review by trying to identify what are the most important way forward for these type of tools to really become a viable and respected alternative to climate models. It's important that these emulators are able to provide those type of variables at the time and spatial scales that our impact models need. So joint variables coherently emulated at a high frequency, daily or even sub-daily. It's important that emulators address variables other than atmospheric variables, that they address the forcings that are not just well-mixed greenhouse gases, but are, either short-lived climate forcers, land use forcing type. We also need that the literature, the authors that propose new emulators conduct a systematic validation of their skills. We need some kind of, agreement across products on what at least a baseline validation should be, and a more clear and systematic descriptions of both, the skills, the limitations, the uncertainty sources that an emulator can address or not. And then finally, especially for this audience, we call for a more coordinated approach to the development of emulators that involve a community like CMIP, where you can think of experiments being designed with emulator development and training in mind, so that we can join forces and apply economies of scale in the type of experiments that we prescribe to the climate modeling community. So I'll conclude here. Maybe I'll put up again the pointer if people want to take a picture, and if there are any questions, I'm happy to answer them. Thank you.
Thank you, Claudia. Has anybody got any questions? Put your hand up if you've got a question, if you want to ask it here, or put a question in the chat. There's one question from Arturo in the chat. He says, what limits there are on spatial resolution from simulations by emulators?
Usually emulators are trained on real climate model outputs. So the limitations are the ones that you can find when you look for climate model output to train your emulator. And it's still a question on how much data an emulator needs to be effective and skillful. And as you know, our climate models that are now getting to be at a very high resolution spatially, of course, are limited in both the number of experiments that they can explore and also the length of their simulation. So it's kind of a trade-off here. You can develop an emulator fairly easily on coarse climate model output. It's still an open question on how well you can train an emulator on very fine resolution, like kilometer scale output. But definitely emulators have been developed for limited domains with a high resolution, and the same is true for time resolution. Or they can be developed by merging observations that are usually at a higher resolution. So I don't have a specific answer, but they are getting there in addressing finer and local scales.